Welcome to this short lecture on designing experiments and presenting data. It pertains specifically to high-performance computing and how to present data in a way that makes your audience understand what you did and probably reproduce your results. Here's what I'm going to do. First, I'm going to show you that it's very important to determine which questions to ask and how to compile, run, and document your code, and so that others can reproduce it. Next question is what and how to measure. There we're going to talk about metrics and how many digits to use and variation of measured quantities. And finally, I'll show a little bit about how to present the data, avoiding blatant mistakes and exposing the effects that you actually want to show. I have to stress that this is all work in progress, and there will be future versions of this lecture that have more data, more examples, and will be more useful. So one word of caution at the beginning. Many students think that the work when analyzing code, looking at performance, analyzing performance of code, the work is done when the data is taken. This is not true. Data taking is just the beginning. You have to communicate the data that you measured. You have to interpret the data, and you have to do that in a way that is interpretable and makes the audience understand what you did and draw proper conclusions from it. So data taking is the start. It's not the end of the story. So first of all, let's talk about questions to ask when doing performance analysis and performance studies on high-performance computing hardware. First of all, what is a scientific question? And here's an example that shows one possible scientific question that we often ask when looking at performance. The question is, does this parallel loop achieve the predicted performance limit on my CPU? Okay, that's a proper question. Of course, it implies that there is a predicted performance limit. Somebody has made some kind of performance model, maybe pen and paper, maybe an automated model. So there is some performance limit I'd like to achieve. I think that could be achieved. And the question is that possible? Okay, that's a valid scientific question that could be answered by taking data and presenting the data in the proper way. The second question is, what measurements do I need to discuss this question and to answer it? And one possible answer to that would be, I need to measure the loop runtime if the program comprises a single loop for each number of cores, for a selected range of number of cores, probably from one core to the maximum number of cores that's useful or sensible on that machine. And third, once I took the data, how do I present the data so that my conclusions are communicated clearly? And here's, I show how this could be done. I could show an XY plot of performance, which is work over time, versus number of cores, because we're dealing with a multi-core CPU. And then I'm plotting performance versus number of cores and comparing it to some model prediction that somebody might have done for the full CPU, in this case 14 cores. So here it's easy to see that my measurement does not fulfill the expectation, and I might want to look into that or interpret this result or discuss it. One word of caution here, there are some objections to drawing straight lines between measurement points, as I did here. I do that usually because it helps the reader to interpret the data, to look at the data. It helps to guide the eye. Of course, it's understood that there are no measurement points between these blue blobs. Okay, the straight lines in between them are just to guide the eye. And then the fourth question, that's very important, not to stop at 3, but really to think about whether the audience or the readers, given the resources, would be able to interpret and reproduce what I did. Okay, so you need to specify the environment, the system environment that you used to make these measurements in the experiments, which means compilers and compiler options, library versions, maybe OS versions, and also all kinds of execution modalities, like how did you pin your threads and processes, which goes under term affinity, rank mapping, number of repetitions, how often did you repeat the measurements, frequency settings, and so on. There are lots of things that can be set and altered in a system before you do the measurements. So these have to be documented so that it is possible, at least, to reproduce the result, and if anything, to interpret it. So here's some general hints, just a list of things that might be useful, and it's not exhaustive. So there are many more things you might want to consider. On a system where modules are used to provide the software to the end users, document the full version of the modules that you used, compile with the optimization flags that's suitable for your system. We usually recommend to use -03-x host, which is a good start for the Intel compiler. Whatever you do, document the flags. Always run with pinning or affinity enforced. So bind the threads and processes of your program to the resources, cores, for example. And if possible, fix the CPU frequency. If that is not possible, you might measure the CPU frequency while you do the run, because CPU frequency, of course, has some impact on performance, and different systems may set different CPU frequencies. So it's very important to document what you did. The best option to choose is usually the base frequency if you can fix it, or the highest supported guaranteed frequency for the instructions that you're going to be using. You might know that on Intel CPUs, for example, if you run AVX or AVX 512 machine code, the CPU might decide to not run at its standard base frequency, but a lower frequency. If you use the Slurm batch scheduler, it is possible to set at least the core frequencies using this command line option to srun --CPU frequency, or use liquid set frequencies if allowed by the system administrators. And it's not allowed always, so you have to see how far you get there. As always, document the settings. Another point, always capture the raw output. Okay, you might have some scripting infrastructure in place that helps you automate your measurements and produce nice graphs. That's fine, you can do that. However, usually in the data taking and filtering process, you throw away a lot of data. And it might not seem important at the moment when you do the run, but more often than not, it turns out later that there's some stuff in the raw files, in the raw output, that could be interesting and could have been mentioned. So always save that for later analysis. And finally, before thinking about setting up a scripting infrastructure to automate all your measurements, perform some manual runs and check the output. Always check that the run performed as expected and did not crash in between along the way, because if you set up a scripting framework to do the measurements automatically, you might collect some data, and then if anything goes wrong from the beginning, all your data is useless, and you burned a lot of CPU hours, a lot of resources for nothing. So please, when you start this endeavor, always perform manual runs and check the output before thinking about automating stuff. So next is the question, what and how to measure? And of course, this is a broad field, okay? It's really hard to say in a general statement, what should we measure? Because there's so much stuff that you can measure. Of course, it depends on what you want to investigate. The thing you start with usually in high-performance computing, this is runtime and other stuff based on it, like derived metrics or work divided by time. But if you measure anything, it's typically the runtime of a piece of code. So how should you do that? And we recommend to write your own time measurement functions. That's what we recommend, as shown here. We have a timestamp function that uses the clock get time with the clock monotonic specifier to take a timestamp. It delivers a double precision value, which is a current timestamp. And if you want to measure the time a certain piece of code takes, you just call it twice and subtract the two values. So here's how you could use it, or probably how you should not use it. We have this simple loop in green. I goes from 0 to n is just 100, summing up some values in an array, sum reduction. And in principle, you would use timestamp like this. You take a timestamp, and then after the code, you take another timestamp. You subtract the first one, and you get the runtime as the difference of the two. So this runtime is what we call a raw metric. You can directly measure it, and it's directly interpretable. From the runtime, you can derive other metrics like performance. Performance is just work over time. What work is in your particular case Well, that's up for discussion. It could be some number of flops. It could be the problem, which then would be 1, and any other stuff that counts as true work. Okay, so that's a flexible thing. That's a moving target. Sometimes, if you do benchmarking, warm-up iterations might be necessary. One example, for example, is MPI libraries. If you have an MPI code, you want to measure its performance, it's a good idea to do a couple of iterations before you do the actual measurement, because the MPI library might take some time to adjust, set up some buffers. The first time you communicate with a new communication partner might involve some additional overhead. So do not start to measure right away, especially if your run is short. Give it some warm-up iterations. One thing to observe, especially with timestamps, and as shown here, is that any time measurement function that you employ has a finite granularity. So in this case, the loop is just 100 iterations long, which means it will be over in, I don't know, maybe 1 or 200 nanoseconds. That's a time span that's very hard to measure with standard methods, especially with the clock get time that we're using here. So in this setup, with this particular example and number of loop iterations, it will not be possible to get proper time measurements. Okay, so this is not only true for time, it's also true for other hardware metrics. For example, energy measurements. With the built-in facilities in modern CPUs, you cannot measure energy or power on a microsecond basis. So what do? Now, for the sake of benchmarking, when you have the freedom to do so, you can set up a little benchmarking harness that repeats the actual benchmark, which is shown as the green loop here, as many times as necessary to get a proper runtime. Okay, so for example, we have this infinite loop here, and we execute the actual benchmark n iter times. Whenever the runtime is smaller than 0.1 seconds, we double the number of iterations. And we do that as long as necessary so that the runtime is greater or equal 0.1 seconds. Okay? And then the whole thing becomes long enough to be measured accurately in terms of time. Of course, in the end, when calculating the performance, we still have to multiply the amount of work with the number of iterations to get the proper performance value, which is full amount of work divided by full runtime. So here's an overview of some raw metrics and raw events that you might want to measure or count. Wall clock time, we covered that. Clock cycles, which is another measure for time. Number of instructions, floating point instructions, mispredicted branches. How often did the CPU predict the outcome of a conditional branch and it was wrong? Okay. Cache line transfers, which translates into how much data was transferred between point A and point B in the cache hierarchy, memory hierarchy. Cache and TLB misses, energy consumption is possible on many modern CPUs, and many more. Okay, these are things that you can measure and count using standard tools like Liquid Perf Counter, PAPI, and others. Now, from these raw metrics and events, which could sometimes be interpreted right away as raw metrics, you can derive what we call derived metrics. And these derived metrics often are more easily understood, more easily interpreted, okay, because they connect better to stuff that you're used to from daily work. For example, you could derive the clock frequency via the number of cycles carried out by the hardware in a certain amount of wall clock time. Okay, that's just the clock frequency. IPC and CPI, or instructions per cycle and cycles per instruction, these are metrics that quantify how many instructions the CPU can execute every cycle. There's typically a limit for that, for the IPC value. CPI is just the reciprocal of the IPC value. Floating point performance, a very popular metric. How many flops does the code do per cycle or per second? It's important because it also has an upper limit. Okay, it's easy to compare the floating point performance of your code or your benchmark with the known upper limit, which is just the peak performance of the device. The branch misprediction ratio. Okay, we can count branches, we can count mispredicted branches, and the ratio of these mispredicted branches divided by overall number of branches, this gives us the branch misprediction ratio. In typical loop-based scientific computing codes, the misprediction ratio of branches is usually small, okay? But it doesn't have to be. Sometimes we have cases where it's relevant. Now, if you count cache line transfers or data transfers, the most important derived metric from these is data transfer bandwidth in bytes per cycle or bytes per second. That's also very interesting because data transfer bandwidths also have an upper limit. Like a memory bandwidth of a CPU could be 150 gigabytes per second, and that's an upper limit. If you measure 140, you know you're pretty close to that. Okay, it's always good to know your limits. And data transfer bandwidth is something that is easily compared with known limits. Cache miss ratios are sometimes very popular. It tells us how many accesses to the memory hierarchy were misses in the cache hierarchy. We're not so enthusiastic about cache miss ratios. We think it's much more interesting to look at data volumes and data transfer bandwidths, because cache miss ratios can easily be misinterpreted. And you could have a code that has a very low cache miss ratio, but it's also very, very slow. Power dissipation in watts is also a derived metric. In modern CPUs, you can measure the number of joules that have been burned by the CPU in a certain time span. And then the power dissipation is, of course, the derived metric, because you divide the number of joules, which is watts times seconds, by the runtime. And of course, many more. Now, when you take data, then your tools usually report the data with some precision, with some given number of digits. And you might not care when you look at the raw data, but when you present the data, it's important to not use more digits than necessary. Usually 3 digits suffice. That's a general rule of thumb. Okay, so here's a typical table that we often see in reports from students. So this student just chose the number of digits that dropped out of their scripts. And of course, that's nonsensical. Okay, if most measurements that you make and also most input data that you have is not accurate to many digits, maybe it's just 2 or 3 or 4 digits. So in the end, 3 digits mostly suffice to convey the message that you want to transmit. Now, if you do measurements, it might happen that the measurements fluctuate. And you all know that computers are supposed to be deterministic machines. When you do something twice and you do the same thing twice, you should get the same answer. This is true for most numerical results, or should be at least, but measurements, especially time measurements and performance measurements, often fluctuate. There's a lot of reasons for that, and I will not go into detail here, but the way that measurements fluctuate is an important element of data taking in high performance computing. So you need to communicate if performance fluctuations from run to run and also from device to device are relevant or not. If you do multiple measurements and then you see that the measurements don't fluctuate by more than less than 1%, you're fine. Okay, you just say that, you communicate the fluctuations are so small as to be unimportant, and you neglect that. If fluctuations are important, as shown here in this graph, include statistical data in your presentation. Okay. And you can do that in a variety of ways. In high performance computing, statistical data sometimes is not normally distributed, and that might be a problem. Okay, as I mentioned multiple times, many metrics in HPC have upper or lower limits, which means if a measurement of such a metric has statistical fluctuations, it's usually not normally distributed, which means then that the average of some multiple measurements may not be a good way of presenting the data. The median may be more appropriate. Okay, and also sometimes you have multimodal distributions, so with several maxima in the histogram, and they can be represented in a variety of ways. So here's an example from a paper. What we see here is the completion time of a given benchmark, in this case HPL, which is the Lindpack benchmark for determining the top 500 rating. And we see a histogram density versus completion time, so how many measurements have been performed with this particular completion time. And you see there's a lot of variation. The overall completion time varies between less than 280 and almost 340 seconds, so which is significant variation. However, the measurements are clustered somewhere around 280 seconds. This is a typical example where measurements are not normally distributed, and there's a hard upper limit, which is, of course, the peak performance of the machine, and Lindpack usually gets very close to that. Now here you see these colored lines show you the minimum measurement, the median of all measurements, the arithmetic mean, the 95% quantile, so the point where 95% of the measurements are left to it, and the maximum. So you might want to pick and choose between these, among these. I recommend to report the minimum, the maximum, and the median. And you see in this example, the median and the arithmetic mean are considerably different. Okay, so there is a difference between median and arithmetic mean. If you want to present that in a compact way, one option is the box plot. In this box plot, we see, for example, that the scientist has chosen the median and the first and fourth quartile in these boxes, and also they present the mean to communicate the difference between median and mean. Another option is the violent plot, or combining the two plots. Actually, I'm not as enthusiastic of the violent plot because it makes you believe that the distribution is smooth, which in fact it's not. Okay, so you have to do some smoothing procedure to get this density function, and the smoothing procedure might remove features of the data set that you might want to see. So I'm much more enthusiastic for the box plot, which just leaves out any speculation, and it shows well-defined quantities like the quartiles and the mean and the median. If you want to know more about data presentation in high-performance computing, there's a very good paper by Hoefler and Belli from 2015, which I highly recommend. All right, so much about data taking, and in the end, once we've took some data, we want to present the data with graphs. And this is a wide field, and there's lots of things you can do wrong. You might want to search for inspiration in a book that I like very much by Justin Zobel, Writing for Computer Science. Especially chapter 11 has a lot of interesting examples, the good, the bad, and the ugly for data taking. And also consider XKCD for inspiration. Okay, so usually in HPC and data presentation for HPC, we're dealing with XY plots. Okay, sometimes we have 3D plots, but most of the data is presented in XY plots. So here's some guidelines how to organize the presentation of such data. First of all, have a meaningful labeling at the axis, including the units. Do not forget to label your axis and specify the units. Provide a meaningful caption that allows to interpret what is seen. I have a good and a bad example later. Give the graph a title which describes the environment, the systems or settings, or provide this info in the caption. So make it clear to the reader what has been done without having to revert to the text, at least extensively. Have a legend. If you've more than one data set, you need a legend to show which color of graph or which symbol type is which kind of data. Start the y-axis at 0 unless there's a very good reason not to. Okay, if you compare values on a y-axis, then the comparison is much more meaningful and much more interpretable if the y-axis starts at 0. Use log scale with care. That's important. Using a log scale can be very useful and instructive if you need to cover several orders of magnitude, but it can also hide important differences. It could diminish the difference, the ratio between two data sets, and it's actually a very good way to sugarcoat your data. And finally, I mentioned that in the beginning, you may use straight lines to connect data points to guide the eye. It's not forbidden, okay, to include straight lines, even though there are no measurements between the data points. It's just to guide the eye. Here's an example. Somebody plotted this graph. The caption was as shown here, scaling on Maggie, okay, whatever. And I now want to walk you through different components of this graph and show you what has gone wrong here. So first of all, the axes are not labeled. It is not shown what units or what quantities are shown on this graph, neither on the x-axis nor on the y-axis. That's not good. Secondly, the y-axis starts at 200 and not at 0, which might not be that bad here, but it makes the data less interpretable because the ratios of different data points are distorted if the y-axis starts at 0. And, well, you might already have guessed that this is performance data, which is higher is better, so we want to compare, we want to describe some sort of behavior of the data. The caption is also really not useful. Scaling on Maggie, what does it mean? Scaling of what? What is Maggie? Okay, so there could be a little bit of more information what's shown here. And then there's a very nice feature in Excel which says connect the data with smooth lines. Okay, so Excel tries to fit the data using some kind of, I don't know, spline function or something. And this is, of course, not good because this indicates or this suggests a smoothness of the data that's just not there. As I said, there are no measurement points between adjacent data points. So this wiggly line in between just makes up data that's not there. It's not just to guide the eye. It's really something that's not in the data. Okay. Don't do that. Okay, all of these things are not good, and there are much better ways to present this data. And it's a very straightforward and simple task to convert this plot into something that's much, much better. So as usual, Randall Munroe has a lot to say about these things, curve fitting methods and the messages they send. So at your leisure, you can study these different options. What do I do if there's a bunch of measurements, certain data set, and I want to make sense of that data set by curve fitting? Lots of options. And he also has this. I clicked smooth lines in Excel. That's what I did in the previous example. Okay. And usually this is one of the worst options that you can choose from. All right. Talking about axes. Here's a published graph comparing the performance of different codes with different compilers, Intel version 13 and PGI version 31. And here comparing two different architectures, AMD PileDriver and Intel Sandy Bridge. So this is from the 2013 timeframe. And this might look very nice. So with Intel, we have a normalized performance of 100%. And with the PGI compiler, there's a lot of gain in performance on the AMD platform. Okay. But if we look more closely, then we see that the scale starts at 85%. And the gain is just 10%. Okay. So by choosing this scale to start at 85%, the maker of this graph has made us believe that the PGI compiler does a much better job than the Intel compiler, while in fact it's just 10%. Again, Randall Munroe has something to say about that. All right, let's go back to our first example. And let's see how we should have presented this data to make it better. First of all, we added labels to the axis. So the x-axis is number of nodes, and the y-axis is performance in gigaflops per second. So an axis label always comprises the metric that we present and the unit that we present. So in this case, gigaflops per second. The caption now is useful, actually. It says performance scaling of the hybrid cool CFD code on Maggie with a problem set A. Okay. Now, how do I distinguish? How do I see whether a caption is useful? Of course, there's a wide spectrum, and there's also some artistic freedom that you can choose from. So the guideline for me is the caption needs to provide the necessary information to allow the reader to connect the presented data to the rest of your presentation or paper. Okay. So if I just write data on Maggie, this is not well interpretable. I have to go back to the text. I have to search for the figure reference and then see whether or not this data is properly described. With a description like this, performance scaling of the hybrid blah code on Maggie with problem set A, if the reader has read the text, then they will immediately connect the data that is shown with the text and what stuff they know from the text. And that's useful in the data presentation. Finally, I'd like to show you to expose some relevant effects and showing what you want to show in data. So what does the user usually want to know? The user of a program for which we measure the performance or other metrics wants to know how long will my problem take to solve? And often people take that literally. Okay, they plot the runtime of a code versus resources like number of cores or number of nodes, number of GPUs. So this answers the question, right? Runtime versus number of cores. Fair enough. However, this kind of presenting data in this choice of graph has some severe problems. First of all, the scaling behavior is hard to visualize. Okay, in the beginning, when we go from 1 to 2 to 4 cores, maybe scaling is quite easy to see because we go down from runtime of 1 arbitrary units to 0.5 to 0.25. So we see the scaling is quite good at the beginning. But at the end, due to the fact that this is a hyperbola in the perfect case and that the measurement points are so close together, it's really hard to see whether there's any scaling from, let's say, 32 to 64 cores. Okay. So I have a lot of space in this graph. The canvas is almost empty. All the data is concentrated in the lower left part of this graph. And I don't use this huge amount of space. I'm compressing my data points in the lower part of the graph here, and this is not useful, okay? I'm not able to discern whether or not there's good scaling or not. Another problem with presenting runtime is that runtime numbers are hard to generalize to different problem sizes. When I say the runtime is 1 second, I mean my problem took 1 second to solve. Now, this is a statement that's very hard to generalize. If another person's problem is twice as big, it may run twice as long, but that's math I have to do in my head or with pen and paper, okay? So there's an extra step to interpret the presented runtime in terms of another problem that some other person has to solve. So it's hard to generalize. It's much better to present metrics that are easier to generalize, like how much work is done in a second, also known as performance. So here's a comparison between runtime presentation and performance presentation. Okay. On the left, again, we have this problem that the interesting data is compressed at the bottom of the graph, especially when it gets interesting with the higher number of nodes. On the right, we see performance versus number of nodes. And our brain is much better to compare stuff with straight lines than with hyperbole, because we know when runtime is plotted over number of nodes and the scaling is perfect, what we see is a hyperbola, basically 1 over x. Okay? But our brain is not good at identifying hyperbole. However, our brain is very good at identifying straight lines. And if code scales perfectly, then performance is linear over the number of nodes. And this is easy to see, okay? And it's also easy to see how far this data set deviates from this linear measurement. So performance is often the superior metric because it's normalized to a defined unit of work, and the scaling behavior is easier to read on a linear graph. Of course, there's also a lot of space here taken up by this graph, and other parts of the graph are empty. Depending on the situation and how you do the measurement, it may also be useful to plot the performance per node, which then would be a straight line for perfect scaling. And if it's not perfect scaling, it's a line with a negative slope. Okay, so there's a lot of artistic freedom that you can choose from. It's not some kind of strict rules here. Try to present the data in a way that makes it useful for the widest possible audience. Another aspect to consider when presenting data is to present it in a way that exposes the interesting correlations and ignores trivial dependencies. This is something that's often done wrong in data presentation. So in this example, we have 2 plots showing basically the same run of the same code. On the left, again, we see runtime. On the right, we see performance of the same code. So in the runtime graph, we run the code 3 times with problem sizes of 500. Don't worry about the exact meaning, 1,000 and 2,000. And obviously, for a larger problem size, the code takes longer to run. This is a trivial dependence. Everybody knows that a larger problem size takes longer to solve. And in this case, the dependency is such that we even need a log scale to accommodate this huge range of runtime. Okay, it's like a factor of almost 30 between the small and the large problem size. But that's a problem because this trivial dependence of runtime on problem size hides the interesting effects. Of course, we see that bigger problems take longer to run. But I don't want to see that. I know that already. What I want to see is there any significant change in behavior when going from small to large problem sizes? And this is hidden by the log scale and this huge range of measurements. On the right, we see performance in iterations per second versus problem size. So here we see much more useful, interesting data. It shows that at problem sizes 501,000, the amount of work that I can do with this code per second is almost the same. There's a small decline, but it's insignificant. But when going to problem size 2,000, there's a strong drop in performance in terms of iterations per second. That's an interesting fact. That's something worth investigating. Maybe there's something with my code. Maybe there's something going on in terms of cache reuse. That's interesting, okay? And this way of presenting the data exposes this problem very clearly. So try to find ways to presenting the data that ignores trivial dependencies of the independent variable, the thing that you set, and the dependent variable, like runtime, performance, or other metrics. Of course, this is highly problem specific, okay? There are no general guidelines here. Just try to think about what should be shown to the reader, what is the stuff that I want to expose, and what is the stuff that is so trivial that I would like to remove it from the graph so that it doesn't disturb my interpretation. Thanks a lot. If there are any questions, please contact me. Have a nice day.